Notes for Section 10 are about Taylor and Maclaurin series. Taylor series are an approach to finding the series for a function using derivatives. Now, the difference between a Taylor series and Maclaurin series is that a Maclaurin series is a special kind of Taylor series. Taylor series can be centered anywhere. Maclaurin series are specifically centered at x equals 0. So someone could say to you, find the Maclaurin series for a certain function, and implicit in that statement is that you center it at x equals 0. We're going to start practicing finding Taylor series with a Maclaurin. So our first example is to find the first 4 non-zero terms of a Taylor polynomial for the function cosine x. And when we say at x equals 0, that means we want a Maclaurin series. What I'm going to do is set up the function over here on the left. So I'm going to set up f of x equals cosine x. Then I'm going to take the derivative. So take the derivative of cosine and we get negative sine. Then we'll take the second derivative. So the derivative of negative sine is negative cosine. The derivative of negative cosine is sine. So how many times do I have to take a derivative? Well, if the math problem tells you what degree of polynomial they want, that's how many derivatives you will take. This math problem does not tell us the degree. It tells us to find the first 4 non-zero terms. So what I'm going to do is I'm going to pause on taking derivatives for just a moment, and I'm going to evaluate the derivatives I have. Where am I centering this polynomial? I'm centering it at x equals 0. So I'm going to evaluate my derivatives at x equals 0. The first one is f of 0 is cosine of 0, which is 1. The next one, negative sine of 0 is 0. The next one, negative cosine of 0 is negative 1. The next one is sine of 0, which is 0. We're going to be looking for these values to use them to set up our polynomial, and 2 of them have zeros, so they won't be very useful. Therefore, I'm going to keep finding derivatives so that I have 4 of them that are non-zero. So let's continue with derivatives. The fourth derivative can be notated by Roman numeral 4 or simply a 4. The derivative of sine is cosine, and the cosine of 0 is 1. Now I have 3 good terms. Let's try the fifth derivative, and if you're following the pattern, we're going to get a negative sine of 0 value of 0. So it looks like we'll need 1 more derivative. The sixth derivative is negative cosine, and the negative cosine of 0 is negative 1. With regard to this polynomial, the fact that we have 6 derivatives here corresponds to the degree of the Taylor polynomial again. So the Taylor polynomial is going to have terms going out to the 6th power. So a polynomial of degree 6 can be set up like this. Constant plus a constant times the first degree plus a constant times the second degree, and so forth. We're looking for a polynomial that would have a 6th degree. Why is it a 6th degree again? It's because we went all the way to the 6th derivative. Now hopefully your math problem will normally tell you what degree to come up with, and that can determine how many derivatives to take. So what I'm going to do at this point is start to take the derivative of the polynomial. The derivative of p is p prime, and you see I'm going to line that up with the derivative of f. So the derivative of p prime will actually eliminate the first constant. So our first term for p prime will be c sub 1. The next term is 2c sub 2x plus 3c sub 3x squared plus 4c sub 4 x to the third plus 5 c sub 5 x to the fourth plus 6 c sub 6 x to the fifth. You can continue taking derivatives just like we did for the function. The second derivative, I'll write it out here. The third derivative is next. The fourth derivative. The fifth derivative. And the sixth derivative. One more step in this table is to evaluate the polynomial derivatives at that location. So evaluate them at x equals 0. And that's not such a bad thing, because when you substitute 0 in for x in the first line, all you get is c sub 0. In the next line, you get c sub 1, and then 2c sub 2, 6c sub 3, 24c sub 4, 120c sub 5, and 720c sub 6. What I'm going to do is set these derivative values equal to each other. So I'm going to go back up in the table, look at the first line. We say that this is the 0th derivative. We haven't taken a derivative yet, so f of x equals cosine is the 0th derivative, and the value of it is 1. So write a 1 down here and set that equal to the value of the polynomial at the same 0th derivative, which is c sub 0. So that's letting us know that the leading constant is 1. Next, I'm going to set 0 equal to c sub 1. Then I'll let negative 1 equal to 2c sub 2. Now that needs to be adjusted. I need to divide both sides by 2, and that tells me that c sub 2 is negative half. Next, we have 0 equals 6c sub 3. Therefore, c sub 3 is 0. Next, we have 1 equals 24 c sub 4, which means the coefficient c sub 4 is 1/24. Then 0 equals 120 c sub 5. Obviously, then c sub 5 is 0. Last one is negative 1 equals 720 c sub 6. So that tells us c sub 6 is negative 1 over 720. Now I can set up my polynomial. The formula was up at the top. In the table, I had p of x equals this polynomial, c sub 0 plus c sub 1 x to the first, and so forth. So now I'm just going to substitute those values in. C sub 0 was 1. C sub 1 is 0, so that's 0 times x to the first. We're going to lose that term in just a moment. The next coefficient is negative half times x squared plus 0 times x to the third plus 1/24 times x to the fourth plus 0 x to the fifth minus 1 over 720 x to the sixth. If I remove the terms that are 0 terms, because the directions asked for the first 4 non-zero terms, I could write it in this fashion. I could write p of x, or the notation generally is using a capital T indicating a Taylor polynomial with degree 6 is 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720. So this Taylor polynomial is an approximation for the series that we can represent with summation notation. It has an alternating component, and that alternating component is positive, negative, positive, negative. So we will assign the exponent of n to that, and the nth term is comprised of an x power on the top and then some type of number on the bottom. The power on the top is going to be x to the 2n. We represent even numbers with the expression 2n. We represent odd numbers with the expression 2n plus 1 or 2n minus 1. In the denominator, the numbers 2, 24, and 720 are actually numbers from our factorial list. So just as a reminder, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720. So you see we have the number 2, the number 24, and the number 720 as our consecutive denominators. So the denominator of our nth term is represented by factorials, and they're even. For the next example, we're being asked for the first 5 non-zero terms of the function e to the x. It is centered at x equals 0. So that means we're actually finding a Maclaurin. I'm going to set up a table and I will write the function e to the x first, and then I'll list the derivatives. I need 5 non-zero terms. So the derivatives are actually going to yield the same function every time. Our polynomial will be a 4th degree polynomial because I have 4 derivatives here. So that polynomial looks like this. I'm going to evaluate the polynomial at x equals 0. When I do that for this line, I'll get c sub 0. The first derivative of our polynomial then is going to look familiar. And evaluate at x equals 0, we will get c sub 1. Let's equate the derivatives. Notice how c sub 2 is 1/2. Notice how c sub 3 is 1/6. Notice how c sub 4 is 1/24. To set up the polynomial, I'm looking at the formula I have in the first row up there. I need c sub 0, and then I need c sub 1 times x. Then I need c sub 2 times x squared, and so forth. Looking at this closer, I'm talking about a Taylor polynomial where I went as far as the 4th derivative, and these terms can be rewritten as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. Now I'm going to look at those denominators. They remind me of the factorials. Remember that 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. And that's enough to be able to set this up with the factorial notation. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And we have to set up the sigma notation for that. So the first few terms did start with n factorial on the bottom, and the numerator will be x to the n power. So that is our sigma notation or our summation notation for this series. The next example is for you. Set up the first 5 non-zero terms of this Taylor polynomial centered at x equals 0 and set up the sigma notation. Pause the video and turn it back on to check your result. Do you remember what the polynomial gives us in the evaluating column? Because if you remember that, you do not have to keep setting up this column anymore. What I'm talking about is this column down here. When x equals 0, and when you evaluate p of 0, you're left with c sub 0. And that's just like the previous math problem. When you take the derivative, you get this polynomial. When you evaluate at x equals 0, you get c sub 1, just like the last problem. The third evaluation, I will get 2c sub 2. So if you remember this last column, you don't need to keep writing out the derivatives for p in this second to last column. That one should be familiar to you. We've worked with that one before. There will be series that repeat themselves in our work, and so it's important for you to have some of the basic ones remembered. The first one we learned of was cosine x, so that one I'm going to look at in this example. The other ones that you'll need to look at are sine of x, which I did not do here, so you need to look at that one. Then there was e to the x, and then the old favorite geometric, 1 over 1 minus x. So if you have these four memorized and you know their series, then you'll have an easier time with Taylor series on the AP test. Watch how easy this goes. If you remember that the cosine series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. Then to figure out cosine of x squared, we just have to substitute in x squared for x. So I'll have cosine of x squared now, and wherever there was an x in the cosine series, I'll put an x squared. So here goes. 1 minus x squared squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial and so on. That means cosine x squared is 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial and so on. And then the sigma notation for that will start with an alternating piece, and it starts positive, so we want an even number power. Then the numerator is powers of x, and they're even powers by a factor of 4. So it's going to be x to the 4n for the power on x. And then our factorials on the bottom are just even powers. So we represent even numbers with 2n, and don't forget the factorial. You are done. No chart needed. Okay, you try one. Do you remember the series for e to the x? If not, look it up and put the series for e to the x here first and then substitute in. Pause the video and then turn it back on to check your answer. And finally, the news you've been waiting for. This theorem says if f has a power series representation at A, so that means it's centered at A, and you have an interval of convergence, then its coefficients are given by this formula. So this formula can take the place of setting up that table. It, however, does not excuse you from taking derivatives. You still need to look at the derivatives. The good news is some AP questions provide you with the derivative values, so you don't have to find them. Looking at this formula, the numerator's notation is asking for the value of the derivative at A. That's what that notation means. And then you know what n factorial means. So the little n up here is what derivative you're on, and A means you're going to substitute in like 0 when it's x equals 0 that it is centered around. Or you'll plug in another number if you're located somewhere else. And that's exactly what's going to happen this time. In our example, we're going to find a third degree Taylor polynomial for 1 over x at x equals 3. So we're finally not going to do a Maclaurin. We're going to look at a Taylor. And I love that they gave us third degree. That tells me how many derivatives to take. So here is our function 1 over x. Take 3 derivatives. And then we need to evaluate them. This time we're not evaluating at x equals 0 though, we're evaluating them at x equals 3 because that's where the polynomial is centered. So substitute 3 in for x. You'll get 1/3 for the 0th derivative. The first derivative will be negative 1/9. Then 2 over 27, and then negative 6 over 81, which reduces to negative 2 over 27. Now I'm going to set up the Taylor polynomial using that formula. Each coefficient is set up by the nth derivative value over n factorial. I'm going to write that down. Nth derivative value. So those are these numbers here in the second column. Here we go. We're setting up a Taylor polynomial. It's a third degree Taylor. The first term is comprised of this coefficient. So that would be our nth derivative value of 1/3. And then the rest of the term has n factorial on the bottom, which is going to be 0 factorial. And don't forget the x component of the term. And you're not just going to write an x, you're going to write x minus 3 because it's centered at 3. Next is the coefficient of the first derivative term, so that's negative 1/9 times 1 factorial on the bottom. And don't forget the x minus 3 to the first power on the top. Next is plus 2/27. The 2 factorials on the bottom and x minus 3 squared is on the top. And then minus 2/27 times 3 factorial on the bottom and x minus 3 cubed on the top. All you need to do is clean that up a little bit, and then we'll come up with a sigma notation. So the first term, I forgot to put the 0 power on this x minus 3 in the first term. That's the 0th term, or the 0th derivative happened there. I apologize. This is just 1/3 times 1 over 1, so it's just 1/3. Then I have 1/9 times the quantity x minus 3, and then I have the 2's are going to cancel in the next term. So we have 2's canceling there. So I have 1/27 times x minus 3 quantity squared. And then in the last term, the 3 factorial on the bottom, that's 3 times 2 times 1. So the 2 in that factorial is canceling with the 2 in the numerator. And I'll have to do 27 times 3 on the bottom, which is 81, times x minus 3 to the third power. So there's your polynomial, t sub 3 of x. Let's set up the sigma notation. I'm noticing we have an alternating series, so I'll put the alternating piece in there. And then we have powers of 3 in the denominator. Do you see 3 and 9, 27, 81? And the first term is when n equals 0, so that's going to be 3 to the n plus 1 power. And then when n equals 1, we will get 3 to the second power, which is 9, so that matches, and so forth. And then in the numerator, we still have the x minus 3 to the n power. So there is our series notation.